All right, advanced placement chemistry. This is our 10th unit. It's called equilibrium. It's chapter 15 in your textbook if you care to refer to your textbook. One thing I'd say about that is you don't need to necessarily, in using the textbook, read every word of every chapter. You may want to just read certain sections that may not have been quite as clear and get the textbook's explanation, or go through and work the sample problems, the example problems. That's always a good idea. To try that and just read them, understand the explanations. So let's move ahead. This is 30 slides. Okay, so equilibrium is the final state of a chemical reaction where the concentration of reactants and products remain unchanged. Some chemical reactions run until all of the reactants have turned to products. So in the example I have here, if you have two reactants A and B that turn into the product C, we've always just assumed that you start off entirely with reactants, so 100% of what's in the reaction chamber, the vessel, is reactants, and then none of it is product. And then by the end, it's all turned into products, so you don't have any reactants left, and all of it is product. Reactions that move only from reactants to products are called irreversible reactions. Very rarely does that happen. It does happen sometimes, but very rarely is it 100% product, zero reactants going to zero product, zero reactants. Let me be sure I said that right. 100% reactants going to zero products, turning into eventually zero reactants and 100% products, but sometimes that does happen. All right, so most reactions can move from both reactants to products and from products back to reactants. These reactions are called reversible reactions and are shown by a double arrow. And again, the way we're going to show it is just this double arrow, but we showed you in class how the arrow is actually usually written, and your textbook would demonstrate the way that arrow is actually written. But it's an arrow or two arrows, one going in each direction. So let's say, for example, you have a reaction where you do have all reactants at the beginning and no products. And then when the reaction has reached its equilibrium, you still have 25% reactants left and 75% products. So that would be the equilibrium state, is 25-75. That means if you started a reaction where you put 90% products into the vessel and only 10% reactants, it would move backwards. It would move to the left, from right to left, so that you ended up with 75% products and 25% reactants. In the reaction above, it doesn't matter whether the reaction starts with 100% reactants and 0% products, or with 10% reactants and 90% products. In both cases, the reaction will stop when there are 25% reactants and 75% products. This is the equilibrium for this reaction. So the example that we used, a simple little example, was a reaction at equilibrium is in a state of dynamic equilibrium. Dynamic equilibrium means that the reaction continues to move back and forth, but does so at equal rates. So if you assume that room A has 12 people and room B has 7 people, 5 people move from room A to room B, and 5 move back from B to A. And then 2 people move from room A to room B, and then 2 move back from B to A. Room A ends up with 12 again, and B with 7 again, even though people move back and forth. So that is what is called dynamic equilibrium. All right, the equation used to measure equilibrium is called the law of mass action. Here's an example of a law of mass action for a hypothetical reaction. Hypothetical just means we're just using imaginary reactants and products, A, B, C, and D there. So if you have 2A plus 3B gives you a reversible reaction producing products C and plus 4D, then the law of mass action is written as follows. So Kc is called the equilibrium constant. The subscript C refers to the equilibrium of a concentration of a solution. You can also have pressures, as we're going to see in just a moment. So what you do is you take the products, the concentrations of the products, they go in the numerator of this ratio, and the concentrations of the reactants go in the denominator. So it's products over reactants. And then the nice thing about this equation is you can use the coefficients as the exponents on those concentrations. You don't have to understand all the mathematics of why this works. Just learn the form and learn how to apply it. The exponents on the concentration of each substance is the coefficient of that substance in the chemical reaction. So there it is. You'll notice another thing, some things that make this different from a rate law. The rate law has rate on the left side of the equation, and then the K, the rate constant, is on the right side next to the concentrations. Another difference is that the rate law only has reactants in it, because the speed of a reaction is only a function of the reactants involved. It's not a function of the products, whereas a law of mass action, in other words, how far the reaction will go towards products or towards reactants, is a function of both the products and the reactants, because it's a back and forth process between those two sides of the chemical equation. So those are the main differences that you'll notice. It's also a capital K for the equilibrium constant, as opposed to a lowercase k for the rate constant. All right, there are several equilibrium constants that we'll be dealing with in the next few weeks. So they are Kc, the equilibrium in a solution measured in molar concentration. Kp, that's the equilibrium of a mixture of gases, so the P stands for pressure. Kw is the equilibrium constant of water, and it's used in acid-base reactions. And it's called a dissociation constant. So you'll hear that word in the next week. Ka is the equilibrium constant of an acid reaction. That's called the dissociation constant of an acid. Kb is the equilibrium constant of a base reaction. That's the dissociation constant of a base. And Ksp is called the solubility product. That's the equilibrium of a salt or other solid dissolved in a solution. In other words, how much of it dissolves and how much of it stays together as the solid. The small letters are called subscripts, and all equilibrium constants, capital Ks, have subscripts. They have to specify what they are the equilibrium of. All right, the law of mass action comes from kinetic rate laws. So there's, again, a law of mass action, a generic law of mass action. So let's look at an actual reaction. Look at the decomposition reaction. So N2O4 breaks into two different NO2 molecules. This is a reversible reaction that can move forward or backwards. Each of these two reactions has its own rate constant. So in other words, we can write each of those reactions as a one-way reaction from left to right. So we do that down below. And actually that should be a single arrow in each of those two reactions down below. So N2O4 goes towards 2NO2. And then you can write it in the reverse reaction, in the reverse direction. 2NO2 goes back to N2O4. So if you wrote the rate law for each of those, you'd have rate equals K forward, rate constant of the forward reaction, times N2O4, that's the only reactant. For the bottom reaction, it would be rate equals K reverse equals NO2 squared. Since it's an elementary reaction, you can use the coefficient as an exponent. And so now you have two rate laws. Since at equilibrium, the rates have to be equal, just like the children walking back and forth between the classrooms, you have to have the same number going in both directions. That means that you can equate these two equations, set them equal to each other, because the rates have to be the same. So if we look up here, at equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. So K reverse, NO2 squared equals K forward, N2O2. If you rearrange them, then put the constants on the same side. So that means you would divide both sides by K reverse. And then you get the concentrations on the same side. That means you would divide both sides by N2O4. Again, it's just a basic algebra maneuver here. You end up with K forward over K reverse equals NO2 squared over N2O4. Since K forward over K reverse, since they're both constants, they will come out to be some other constant, whatever that number happens to be. And we call that new constant the equilibrium constant. So that's how you use the laws of kinetics that we studied in the last week with the law, with the equilibrium constant. This means the equilibrium constant Kc equals the ratio of the rate constants for the forward and reverse reactions. The larger the value of Kc, the more the reaction moves in the direction of the products. And that makes sense if you look up above K forward. If K forward is bigger than K reverse, a lot bigger, that means the reaction is going to move in the direction of the products. If K reverse down on the denominator of that ratio is bigger than K forward or a lot bigger, then that means that the Kc is going to be very small, and that means the reaction tends to move backwards towards the reactants. So large Kc means more reactants turn to products. Small Kc means more of the reactants stay as reactants and don't turn into products. Or if they're already there as products, they'll move backwards and turn back into reactants. All right, equilibrium constants do not have units. So an example, write the equilibrium constants for the following reactions. So just convince yourself that those would be the laws of mass action for those particular reactions. But there's no constants to an equilibrium constant. It's a dimensionless or unitless variable. All right, there are equilibrium constants for equations expressed in terms of gas pressure rather than concentrations. And pressures work exactly the same way as concentrations mathematically, it's just written a little differently. As you see the law of mass action written over there on the right-hand side, it's written as pressure, capital P, and then whatever the compound or element is or substance is, you write that as a subscript of that P, and you can put it in parentheses like that. So it's just the form that you write it. So that's the law of mass action for a reaction that's in gases rather than in solution. There is a way to relate the equilibrium constant for a concentration to the equilibrium constant for a pressure. It involves the ideal gas law. So using the ideal gas law, PV equals nRT, and the equation, an equation relating Kp to Kc can be derived. You should know the equation, but not how it's derived. You don't even really have to have it memorized. But it is something you should know how to use. So in this case, the R value, the gas constant, is the one that we use for PV equals nRT. It's 0.0821. And the temperature is measured in Kelvin, and delta N is the change in the number of moles from reactants to products. So if you looked at the reaction up above, if you see on the left-hand side, the reactant side, there's 2 moles of A and 3 moles of B. That's a total of 5 moles. And on the right-hand side, the product side, there's 4 moles of C and 5 moles of D. So that's a total of 9 moles. So the change in moles is going from 5 to 9. So that number would be 4. The change in moles would be 4. It's just add up how many moles of each reactant and product you have, and it's just whatever the change is. All right, equilibrium follow a few basic mathematical rules. So rule 1 is when a chemical equation is reversed, the equilibrium constant becomes the reciprocal of the original constant. So when we turn the reaction around from A plus B goes to C, back to C goes to A plus B, then the equilibrium constant becomes a reciprocal. It goes from 2 to 1/2. It's not like Hess's law with enthalpies where you put a negative sign on it. It's not that at all. So don't get the two confused. All right, equilibrium follows a few basic mathematical rules. Rule 2, when a chemical equation is multiplied by a factor, that is just a number you multiply through by a number, the equilibrium constant is raised to the power of that factor. So for example, if the reaction below is multiplied by 2, then the equilibrium constant is raised to the second power. So you can see that happening right there. So the original equation has an equilibrium constant of 3, and when you multiply through by 2, then you raise 3 to the second power to get 9. Rule 3, when two equations are added, then the equilibrium constants are multiplied. So if you took those simple equations A to B and the second reaction C to D and you added them, so you have A plus C produces B plus D, then what you do to their individual equilibrium constants is you multiply them to get the equilibrium constant for the combined reaction. So these are just some basic rules to know and to learn as to how equilibrium constants change when you change the equations in some fashion. All right, homogeneous equilibrium means that all of the products and reactants are in the same state. So in those two examples, you can see that everything in the first reaction, A plus B goes to C plus D, is all aqueous. In the second reaction, A plus B goes to C plus D, is all gas. Those are called homogeneous equilibria. And they do at times have special properties versus when they're heterogeneous and aren't all the same state. We won't talk about that now. Just know that the definition for right now. Whenever a pure liquid or a solid appear in a chemical equation, they are not included in the law of mass action. So in this reaction, PbCl2, which is a solid, produces Pb2 plus and Cl2Cl minus. Then the law of mass action is Kc equals Pb2 plus Cl minus squared. You notice you don't see PbCl2 because it is a solid, so it does not appear in the denominator. Okay, so there's the same example up on the top of this slide. Down at the bottom, there's just the alternate example. If you have hydrochloric acid in water, it produces hydronium and chlorine in aqueous solution. So everything there is aqueous except the water, H2O, which is liquid. That's a pure liquid. And therefore, you include all the three aqueous substances in the law of mass action, but you do not include the water because it's a pure liquid. All right, so here's an example. It's a pretty simple example. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at a certain temperature. The only significance of the temperature is that the temperature stays fixed. If temperature changes, then that changes all the properties of the reaction, and you can't apply the same formula. They're not going to throw you a curveball on the AP where they do that, but they just want you to know that you have to state that it is at a certain temperature. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres of H2, 2.46 atmospheres of N2, and 0.166 atmospheres of NH3. From these data, calculate the equilibrium constant for the reaction. So first of all, you simply write the law of mass action from that reaction, and then you plug in the pressures that they've given you, and you do the math, and that's all there is to that. That's how you would get the equilibrium constant for the pressure. The equilibrium concentrations can be found if at least one reactant or product are known. This is done using an ICE table, sometimes called a RICE table. So an ICE table showing the initial beginning concentrations, the change in concentration, and the equilibrium, which basically is the ending concentration, is shown below. And sometimes they do include the word reaction to make it a RICE table, but more often it is called an ICE table. So what it has is, on the top line, it has the actual reaction. Usually don't include the arrow as I did in this one, but just to distinguish between where the reactants are and where the product is. And then down below, you have some spaces to fill in. And we'll have a lot of practice in the next week filling in those spaces and how that's done. It's really not that hard. It just takes a little practice. Example of using an ICE table: a closed system initially containing 1 × 10⁻³ molar of I2 and 2 × 10⁻³ molar of H2 at 448 C is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI, that's the product, is 1.87 × 10⁻³ molar. Calculate the equilibrium constant of concentration at 448 for the reaction. So they state that the temperature has not changed. You don't need to use that number in the problem. You just need to know that the temperature remains constant. They could have just said that. Okay, so for the initial concentrations of the reactants, we have them up on the initial line. It's the 1 times 10 to the minus 3, 2 times 10 to the minus 3. And then it says that the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the minus 3. So that goes down on the equilibrium line. All right, so it's just like a little puzzle where you have to fill in the blanks. So where is a blank that you can fill in? Well, let's go ahead and check this out. So the first thing you can see, obviously, that I think that all of you can see you can fill in, is you can fill in the 1.87. So what you're doing is taking the initial line and either adding or subtracting the change to get the equilibrium. Now, if it's a product, products are increasing, so therefore it would be an addition. If it's a reactant, reactants are decreasing, as we know. They decrease as a reaction goes from left to right, as it goes in its normal progression. Therefore, that would be a subtraction on the H2 or I2 columns. But for the 2HI column, it's going to be an addition. So we add 1.87, 0 plus 1.87 times 10 to the minus 3, gives us the number they told us we had, 1.87 times 10 to the negative 3. Okay, so since you know the initial and equilibrium values of HI, you can calculate the change, which is 1.87 times 10 to the negative 3. All right, so we work backwards now and fill in the change for the two reactants. So if 2 moles, look at the relationship up at the top in the reaction line or in the equation. 2 moles of HI relates to 1 mole of I2 and 1 mole of H2. So it's a 2-to-1 relationship. So if 1.87 times 10 to the negative 3 represents 2 moles, then half that number is going to represent 1 mole. So we work back to the reactants, and half of 1.87 is 0.935 times 10 to the minus 3. And because it's a reactant and it's being consumed, we put negative signs. That's going to be subtracted from our initial concentration because the concentration of reactants is going down. And if you do those two subtractions for H2, you end up with 0.065 times 10 to the negative 3. And although it's covered up a little, you can see that for the I2, it's going to be 1.065 times 10 to the negative 3 in the equilibrium. So that's ultimately what we're trying to find out in most problems, is what are the equilibrium concentrations or pressures, if it's gas, of the different reactants. And then, so using the ICE table, we were able to do that. And down below, it just shows the calculation that got us there. So both of these reactants are decreasing in value, so a negative sign is placed in front of them in the change row. All right, so now what we have is we can go ahead and write a law of mass action using the chemical equation up at the very top. And this just shows that subtraction that we just talked about just a moment ago for H2 and for I2. Okay, so the law of mass action is going to be HI squared over H2 times I2 concentration. So that's just writing the law of mass action in general form. And now what you can do is, to get the equilibrium constant, to get an actual numeric value, is just plug in the numbers. Plug in your concentration of HI at the top for the products, and plug in your concentrations of equilibrium concentrations of H2 and I2 on the bottom, and just do the math, and you end up with 51. So the equilibrium constant for this would be 51. Okay, what is a reaction quotient? The reaction quotient, Q, is computed the same exact way as an equilibrium constant, K, except Q is computed using existing, not equilibrium concentrations. So right here, if we go back to the previous slide, we computed K using the numbers down on the equilibrium line. But what if we started off the reaction with some other number of concentration, some different number than those of concentration? So we see that the equilibrium in this equation, in this reaction, is 0.065 for H2, 1.65 for I2, this is times 10 to the negative 3, and 1.87 times 10 to the minus 3 for the HI. So what if we had concentrations other than those? Then that would be how you would calculate Q, and by comparing Q to K, you can tell which way the reaction will move. So the reaction quotient is used to tell which way the reaction will flow. If Q is equal to K, then the reaction's at equilibrium. Everything has got to be exactly the same. If Q is less than K, the reaction has excess reactants. It means the denominator of that law of mass action is bigger than the numerator. It's too big for the numerator, and that means you're going to flow from reactants to products. So you're going to start forming products if Q is less than K. And finally, if Q is greater than K, that means the numerator is bigger than it should be for equilibrium. So that reaction is going to flow in the reverse direction. It's going to go from excess products back to creating more reactants. So the reaction quotient Q is computed the same way as the equilibrium constant K, except Q is computed using existing, not equilibrium concentrations. So the reaction from the previous example begins with the equilibrium concentration shown below. So these are the exact same numbers you had in the equilibrium ice table just a couple of slides back. But we're going to change the concentration of the product. It's greater than it was in the example before. The previous example, it was 1.87 times 10 to the minus 3. Now we're saying we have too much product in there. We have 2.5 times 10 to the minus 3. So what do? We compute Q the same way that we computed K. So you plug the numbers in, and what you end up is a Q value of 90. Remember, the equilibrium K value was 51. So since Q is greater than K, Kc was 51 from the previous example, the reaction will move in the reverse direction to reduce products and create more reactants. So the reaction will move backwards. Okay, finally, we're going to talk about Le Chatelier's principle. Le Chatelier's principle states that if a chemical system is at equilibrium, is disturbed by a change in either temperature, pressure, or concentration, in other words, you do something to throw it out of equilibrium of one of the components, the system will shift its equilibrium so that it counteracts, that means works against the effect of the disturbance. So it wants to put itself back in equilibrium, so it's in balance again. By the way, a couple terms that we talked about in class. If the reaction changes so that more products are formed, it is said to favor products. If the reaction changes so that more reactants are formed, it is said to favor reactants. So get used to using those terms. That's appropriate terminology in this subject. All right, so examples. The reaction below is initially at equilibrium. If reactants are added or products removed, so that means if you either added more H2 or you added more I2, or you remove the products, there should be an arrow between those, so that you reduce the amount of HI, the reaction will move towards products. It will have too much reactant for the amount of product if you do either of those two things, either add reactants or remove products. And therefore the reaction will shift to the right. It'll shift towards HI. If reactants are removed or products are added to the reaction, it will move the reaction toward reactants. So in other words, you put more HI in than it wants to have at equilibrium, it'll start decomposing that HI into H2 and I2. Or if you remove some of the H2 and I2, there won't be enough for it to be in equilibrium. So it'll start to move where there's less HI and more H2, I2. It's very logical when you think about it, how this principle works. So add HI, H2, I2, remove HI, that favors the products. Remove H2 or I2 or you add HI. You do either of those. You don't have to do both of them. And that's going to favor the reactants. Okay, now we're going to talk about how a temperature change will affect the reaction that's in equilibrium. In an endothermic reaction, heat is treated as a reactant, and heat added pushes the reaction to favor products. So an endothermic reaction means heat wants to go into the reaction to make the reaction happen. So if you were to prevent heat from going in, the reaction really couldn't happen because it needs that heat to go from reactants over to the right-hand side of products. So we treat heat as though it's a reactant, just like it's H2 or I2. And that's a delta H, a positive delta H is endothermic. So what that means is, If you add heat to an endothermic reaction, which likes heat and wants heat to be able to make the reaction go forward, then that'll favor the products. It'll produce more. In an endothermic reaction, heat is treated as a reactant, and if heat is removed, it pushes the reaction in favor of the reactants. In other words, the reaction can't go forward if you take heat out of the room because it needs heat to go from left to right. So if you remove heat, it's going to go in the opposite direction. You're going to have less HI and more H2I2, and that's again for an endothermic reaction if you remove heat from the reaction. So removing heat favors the reactants. Okay, now here's an example of an exothermic reaction. That means heat wants to leave the reaction. It wants to get out of that reaction and go out into the surroundings, into the room. So heat is treated as a product that's on the right-hand side of the equation, and heat removed pushes the reaction in favor of products. In other words, this reaction wants to give off heat. And so if you clear that heat out of the way, then more heat can come out. And so if you remove heat, then it will be easier for heat to escape from the reaction. The way I think of this is if the room is really cold, then more heat will come out of an exothermic reaction, which gives off heat. If you turn the temperature up to 500 degrees in the room, it's hard for the heat to escape because the room's already too hot. So that would be adding heat to an exothermic reaction, and that slows the reaction down. Okay, so heat removed is going to favor the products. It's going to move towards HI. In an exothermic reaction, heat is treated as a product, and heat added makes it more difficult for heat to exit and pushes the reaction back in favor of the products. So it's basically what I just explained. If you add heat to a reaction that wants to give off heat, then the reaction is not going to work very well. So it wants to go backwards to favor the reactants. Okay, so in an exothermic reaction, heat is treated as a product. Heat removed pushes the reaction in favor of products. And exothermic reaction, heat is treated as a reactant. Heat is added, pushes the reaction in favor of the products. Okay, so we said that. All right, now with pressure. Well, there's different ways you can increase or decrease the pressure in a chemical reaction of gases. One of them is to increase the temperature, but we already talked about the effect that has on an equilibrium. Another is to increase the number of moles of substance. In other words, if you pack more molecules into a certain amount of space, that'll increase the pressure. But we already talked about that when we talked about concentration. So the only one we haven't talked about is what if you have a pressure increase or decrease as a result of changing volume. So go back to your PV and RT equation, and what does changing volume do? Well, if you reduce the volume, you're going to have to increase the pressure if everything else is held constant. In other words, you're squeezing the molecules, the gas molecules, into a tighter space, and therefore they have higher pressure. So let's take this simple reaction, simple decomposition reaction. Well, it has 1 mole on the reactant side, N2O2, and it has 2 moles on the product side. That's 2 moles of NO2. So there's twice as many moles on the product side as on the reactant. That means if this reaction runs entirely from reactants to products, you're going to go from having 2 moles in your container, going from having 1 mole in your container on the reactant side to having 2 moles on the product side. So if pressure is increased, the reaction will try to return to equilibrium by reducing the number of moles, which reduces the pressure. Think about that. 2 moles is going to have more pressure than 1 mole because there's twice as many molecules inside of the container. So they're going to hit the sides more frequently and produce more pressure. So if you suddenly increase the pressure by squeezing down the volume, then it wants to go back in equilibrium by reducing the pressure. It wants to go back to where it was before. And the way it can reduce the pressure is by taking those 2 moles and converting them back into 1 mole. If you have fewer moles, you have less pressure. So the reaction will run in the reverse direction. It'll run from 2NO2 backwards to N2O2. That's if you increase the pressure. If the pressure is decreased, and you would do that by expanding the volume so the molecules don't hit the side of the container as often, there's less pressure. The reaction will try to return to equilibrium by increasing the number of moles. So if you put more moles in the container, you'll have higher pressure. And how does it do that? It does that by moving from left to right, from reactants to products. So it goes from having 1 mole of N2O2 to 2 moles of NO2. So it increases the pressure by increasing the number of moles. So this can be done by turning reactants into products. That's 1 mole to 2 moles in the reaction above. So increase in pressure favors the side with the fewer moles. It's not necessarily the products or reactants that get favored in general. It's which side has the fewer moles when you increase the pressure. And a decrease in pressure will favor whichever side has more moles. So there it is. Increased P increases the side with fewer moles. Decreased P increases the side with more moles. Finally, we'll just touch on catalysts. We talked about that in kinetics and how it works inside of a chemical reaction. Equilibrium exists when the rate of the forward and reverse reactions are equal. This will happen at a particular activation energy represented by the highest point in the reaction pathway. When a catalyst is used, the activation energy of the reaction is lowered. Lowering the activation energy increases the rate at which reactants are converted to products, but not the amount of reactants to products. So the key takeaway from this slide is catalysts do not change the value of the equilibrium constant. They do not change how much product you're going to end up with or how much reactant you're going to end up with. They simply determine how fast that reaction takes place. But you'll end up with the same amount of product and the same amount of reactant with or without the catalyst. Okay, so that concludes the slides, just a little under 40 minutes. So I want you, any notes that you take on these slides you can use on the quiz. I think it's going to be about an 80-point quiz. That's half a test. That's a lot, but I want you to get this material down tonight, and we need to really move into this quickly in these last 9 days. So this shouldn't be too hard to do, and go ahead and take whatever notes you want. You can use those on the quiz tomorrow. Okay, so have a good evening, and we'll see you in class tomorrow.